Okay, let's talk pretty briefly about inductors. It's something that we didn't get to cover in class pretty much as I'd like to, and so I'd like to make certain that you have at least some understanding of what they do functionally. Now, we'll still apply a lot of the other physics in order to use them, the things like Kirchhoff's loop rule, junction rule, a lot of all the other things that govern circuits still come into play. And inductors, the way that they function is they use a lot of what we learned with magnetism. In short, what an inductor is, it normally goes into a circuit. Here's our voltage source, our wire, and then an inductor is usually done by a curvy loop like that, and then we'll have maybe a resistor over here. So this is what we would call an LR circuit. Just like we had an RC circuit for resistors and capacitors, this is going to be a resistor and an inductor. Now, one of the things to get used to is when you're dealing with inductors, they're pretty much always marked with a capital L. Okay? So, what you're going to do is, pardon me, let's talk a bit about what the inductor does, what it is. This coil here is actually very descriptive. It's very similar to our coil of wire here when we're looking at induction, hence inductor. What happens is these guys are rigged up such that when we close the circuit, we flip our switch, and we have current come out of the voltage source, it all starts moving at once, right? The current, as it's trying to come out here, everything has to move in turn. So it's basically instantly the current starts moving throughout our entire circuit. The inductor is set up where as the current starts to come through, if we have the current changing a decent amount, then it'll create a changing magnetic field, right? So if I start off with no current and then I have a little bit of current start come in, I go from zero magnetic field to a pretty light magnetic field. And as that current tries to go up higher and higher, I have an induced, a changing magnetic field. Well, that changing magnetic field can induce an opposing current, right? Because when you've got loops of wire like that, nature tries to, it doesn't like change, so it's going to avoid, if you have a change in flux as your magnetic field gets stronger and stronger, it's going to induce a current opposing that so that it's not actually changing all that much. So what this serves to do, this is basically a throttle control on your current. When you connect this initially, it only lets a little bit of current go through, and then over time it starts letting more and more go through. As we get more current going through, the amount that it changes is a little bit. So going from 0 to half an amp, for instance, would make a big difference in the magnetic field that you would get going from a 0 magnetic field up to, I'm not going to run the numbers right offhand, but the magnetic field that you get. But later on, if you go from like 2 amps to 2.5 amps, the same actual change in amperage, right? Only half an amp, but it's a much smaller amount compared to what you totally have out there. It's not a huge change in the strength of your magnetic field. As a result, as more and more current starts going through, the resistance, the impedance that this inductor provides will actually start tapering off because your magnetic field strength isn't really changing all that much. And so it will taper off in, again, an exponential decay. But basically, you can imagine this as kind of a throttler. Basically, you connect your circuit, and it says, no, 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 no. You don't get to have all the current coming through at this instant. We're going to let a little bit more, a little bit more, a little bit more go through, which can be good. Some components don't react well to getting all of the current right there in an instant. It can be nice to have it come out more slowly. It will also, what it does is as more of this goes through, it will induce a magnetic field in here, because this is basically a solenoid. It's a looping of wire, for want of a better term, right? And so we will induce a magnetic field. It will actually begin to store energy in this inductor. It'll take all the energy that the battery is giving out at the beginning, because we have very little current going through our resistor at the beginning, so we're not using much of that power, that energy that the battery is giving out. So it's got to go somewhere, because we have a loop rule to satisfy. It ends up going into the inductor. We're actually charging up, effectively, the inductor. But instead of charging it with charge, we're actually storing the energy in a magnetic field. Because what's going to happen is once we get the magnetic field good and solid and we get to our maximum current after a lot of time, then when we turn off the circuit, the inductor says, oh no, now all of my magnetic field is gone. I don't want that to be the case. I oppose change, so I'm actually going to begin releasing that energy. I'm going to start inducing a current to try and get some of that magnetic flux back. And it will slowly let that energy out. Now the important thing that we get from this, one of our equations, the energy stored in an inductor, so we'll call that potential energy of an inductor, L, capital L, again, tells you you're dealing with inductors, equals 1/2 L I squared. Where this is 1/2 our inductance, which is a lot like the capacitance. It describes how good of an inductor this thing happens to be. Or for resistors, we had resistance. It describes how good it is at its job. Times the current, our final current there, or the current going through it at the time, I should say, our current squared. So this is another one where we see our current come into play. So this is one where in combination with our current equals dq dt, we might actually piece together a differential equation. Though not as likely since this is our full potential energy, and normally we get these guys pieced together by setting up Ohm's law. Just like in mechanics, we usually got our differential equations by setting up Newton's law, second law. Okay, so this gives us one of the important things. Our inductor, like our capacitor, actually stores energy. Pardon me. And so it will release that after we turn off or break the circuit and basically remove our battery. We'd need a complete circuit for it to begin to discharge, just the same as we had the capacitor. But we could charge that guy up and he would store that energy in a magnetic field. Now the important thing for this is, because as I said, this is one of the other places where you can end up with a differential equation for your circuits. We need to know something where we can use Ohm's law. That's how we normally set them up for circuits, right? So we need to know the voltage across an inductor. Now, normally, since this is an inductor, we're talking about changing magnetic fields. I'm about to have students come in. Changing magnetic fields, which is equal to our EMF. I told you that that functions you would choose now to go out on me. Seriously? Come on board. EMF, which is effectively our voltage, it is going to be equal to this. Negative L di dt. There's our differential equation for our inductors. Okay? So, you would use this, your voltage. This would go into your loop rule, which is one of the ways that we get everything set up. And you're using replacements with Ohm's law. I'm sorry, I kept saying Ohm's law, but I meant loop rule. Double check some of the stuff that we've done. And you'd have this guy in, because in a closed loop, your voltages have to be 0.